Enthalpy, again, has the symbol delta H. And if the Q's we talked about so much in the last section are at constant pressure, Q sub P is delta H. But anyway, delta H sometimes has a little superscript 0 there, like a degree symbol. And that just means standard conditions. And for enthalpy values, as well as other thermodynamic, that means you're going to have somewhat relatively constant kind of conditions. So the pressure will be about an atmosphere, which is the pressure normally that things are done at. Concentration, 1 mole per liter. Temperature, about room temperature, 25 degrees Celsius. And also you're going to have species in standard states wherever possible. So oxygen's normal state is a gas. That's what you're breathing in right now. You can have, for example, liquid oxygen, but that's really weird. You can also have ozone, which would kill us, so there's not a lot of that around. Standard states just means the most common. So for carbon, that would be graphite, not diamond. Darn it, diamonds are more expensive, obviously more rare and stuff like that. So if you see a little 0, just means standard conditions. Thermochemical equations are really just another kind of chemical equation, but they've got the energy associated with them. All right, so notice this first reaction right here. This is methane and 2 O2s making CO2s and 2 waters, and the delta H here, it claims under standard conditions, negative 802 kilojoules. So again, if the delta H is negative, that means exothermic. Now, exothermic means that energy is given off by the reaction. So an alternative way to write an exothermic value is to actually put the energy in as a product, because if energy is being released, it's going to be a product, all right? So exothermic energies, you can actually write them into a chemical equation as an energy term. So exothermic energies will be showing up as a product. It's a positive number, but because it's a product, that means it's released, just like the CO2 and water. That 802 number is helpful. So that means that for every 1 mole of CH4 that's consumed, you're going to have 802 kilojoules of energy released. Also, though, you can do it for products. For every 2 moles of water that are produced, you're going to have 802 kilojoules of energy released. So these equations can be super helpful, all right? If you want to know the energy that's given off by making, say, half a mole of CO2, well, 802 kilojoules of energy released per mole of CO2. And if you're only using half a mole, 802 times 1/2 would be 401 kilojoules of energy released. So very, very helpful. So again, delta H negative, you put those in as a product. You can probably imagine if you had a delta H which was positive, those values would go in as a reactant. The standard molar enthalpy of combustion of propane, which is used in barbecues and stuff like that, negative 2044 kilojoules. And there's the reaction. C3H8 is propane. It reacts with 5 O2s to make 3 CO2s and 4 water. Is the reaction exothermic or endothermic? All right. Well, negative enthalpies, negative numbers like negative 2044, that means, once again, exothermic. All right. And if you wanted to, because it's an exothermic reaction, you could write plus 2044 kilojoules right there, all right? And that would be another way to express that negative delta H. And sometimes one way is easier than another. It's just another tool for your arsenal of chemical things to do. Here's another example. How many kilojoules of energy are released when 128.5 grams of methane, CH4, are combusted? And here's the reaction. So CH4 and 2O2 make CO2 and water. Delta H again, negative 802 kilojoules. So what we're going to do in this problem is we're going to turn the grams of methane into moles using the molar mass of methane. And finally, because 1 mole of CH4 releases 802 kilojoules, kilojoules, we can actually use this to find the enthalpy. It's not too difficult. So again, grams to moles are the first part. CH4 is about 16.04 grams per mole, and that came from carbon, about 12 grams per mole in the periodic table, plus hydrogen on the periodic table is about 1 times 4. It's about 16. You can do better sig figs than I just did. But anyway, we're turning grams of methane into moles of methane. And then that negative 802, that means you've got negative 802 kilojoules per reaction. And there's one methane, there's one CH4 in this reaction. So you can literally multiply the moles times negative 802. You're going to get out negative 6.43 times 10 to the third kilojoules. People that study the efficiencies of fuels will do this kind of process. They'll turn so many grams into moles and then multiply it by the delta H to find the energy released for so many grams, so many moles, stuff like that. Pretty cool. In this question, it says how many kilojoules are released when 32 grams of oxygen are combusted. So in this thing, what we're going to do is we're going to turn 32 grams of oxygen into moles of oxygen. There are 2 moles of O2 per reaction. So you can think about that, if you want, as negative 802 kilojoules per 2 moles of O2, if you'd like to. But anyway, here's what the math looks like. Grams of O2 to moles of O2. 2 moles of O2 will release negative 802. And again, that comes from this 2 up there and the negative 802 right there. Negative 401 kilojoules. Quite a bit of energy released. If you have a reaction like this one, hydrogen plus half an oxygen making water, and you end up with a delta H value of negative 242 kilojoules, there are different ways to manipulate these equations to fit what you're looking at the time. All the delta H values depend on how the reaction's written, and it also depends on the phases of reactants and products, like do you have H2O gas or are you making H2O liquid, for example. So here's an example. The first one, H2 plus 1/2 O2 making water, got those crazy fractions, and I really dislike fractions, as I've told you before. So let's say I said, oh, get rid of those fractions. Well, you'd multiply the whole equation by 2. You'd have 2H2 plus O2 making 2H2O, and the new delta H2, would be nothing more than the old delta H times 2. So negative 242 times 2 is negative 484. So if you multiply the equation through by 2, you multiply the delta H by the appropriate part. If you went from delta H2 back to delta H1, you would multiply everything through by 1/2, and you take half of 484 to get negative 242, etc., etc. Let's say that we're going to flip the reaction. So H2O gas is no longer a product, now it's a reactant. And we're curious how much energy is going to happen if you take that water gas and you make it into hydrogen and half an oxygen. Flipping an equation means you're going to change the sign. So what was a negative 242, becomes a positive 242. So flipping the equation, reactants to products, products to reactants, you have to change the sign. Same magnitude, but opposite sign. Goes from exothermic to endothermic. And then finally, the phase does make a difference. So all the above examples have been for H2O as a gas. Well, what if you wanted to make H2O as a liquid? All right. Well, if you calculate it, and I'll tell you how to do that here in a little bit, it comes out to be negative 286 kilojoules. This is different than the first one. Right? It's not the same value. It's a totally different value. And we'll talk about how you can calculate that in a little bit. So the type of phase makes a big difference, and the directionality. And there's things you can do with it, and that's kind of cool too. How do you go from H2 and O2 to, say, liquid water, if you know water vapor and stuff like that? Well, one way to do it is to do this in 2 steps, all right? You can first calculate the hydrogen and oxygen transformation to water as a gas, and then you can study the water as a gas to water as a liquid transformation. Both of these we're going to see are exothermic, which is going to be nice. If you look these up in tables, all right, the first reaction, H2 plus 1F O2 making water gas, that's a 242 kilojoule transformation. Now, it was a negative 242, so I'm writing it as a product. I'm writing it as plus 242. Remember, if the energy is on the product side, that means it's exothermic. Now, gas water to liquid water, if you look this up, is also exothermic. It's 44 kilojoules of energy released. But what we want to do is we want to go from H2 and 1/2 O2 directly to H2O liquid. And if you look at these two things carefully, there's an H2O gas on the product side here and an H2O gas on the reactant side here. So let's add the equations up. And if you do that, you can cancel H2O gas from both sides. If you have an X on the left and an X on the right in math, you can subtract X from both sides and get rid of it. That's what we're going to do here in chemistry. So we end up with H2 plus 1/2 O2 making H2O liquid, and the energy that comes out of it is nothing more than adding up the two individual energies. So 242 plus 44 is 286 kilojoules. So we took two known equations, we combined them together to give us an overall third equation, which we didn't know before. And this is an example of what's called Hess's law. And Hess's law says that if you have known equations, you can add them together in order to give the delta H of a new equation. And Hess was the first person to figure that out. And it was kind of clever what he did. Thermodynamics is really interesting how you can do these kind of processes. And we'll see how Hess's law can be helpful when it comes to these kind of problems. Let's do this reaction. This is 3H2 plus N2 going to 2NH3. And we really want to know what the delta H of this reaction is. Okay, so here are two known equations, all right? This one is for making a compound called hydrazine, N2H4, which is kind of weird. And hydrazine reacts with hydrogen to make ammonia. So you can see that there are some similarities between these reactions, but there's also some differences. But the important part for us is that some scientists figured out what the delta H's are of those two individual reactions. So Hess's law, what you can do is add two equations or more than even two equations together to give you the desired equation. And remember, this up here, the one in bold, that's the reaction that we're looking for. What you can do is add equations 1 and 2 together. So all of the reactants, 2H2 plus N2 plus N2H4 plus H2, you put them all together on the same side, all right? And, oh, I forgot to underline that one, yeah. And then on the product side, you add all the products together. So N2H4 plus 2NH3. And like we've seen before, if you have things that are similar on both sides, you can get rid of them. N2H4 is the same on both sides. You can also combine the H2s together. And if you do that, first of all, the N2H4 cancels, the H2s combine, you end up with 3H2 plus N2 making 2NH3. And that's the equation we wanted. But we really want the energy, the delta H of this reaction. So in this particular example, what we want to do is literally just add those two delta H's together, delta H1 plus delta H2. And if you do that, delta H of the desired equation, negative 92.2 kilojoules exothermic. So notice in Hess's law, you have to know what the desired equation is. That's always a given. And your goal is basically to take the given equations with their delta H's, which are these two right here, and manipulate them in ways to get the overall equation. In this one, we just added them together. Now remember, you can flip equations around too, and exothermic reactions become endothermic, etc., etc. You can also multiply equations by like 2. If you do that, then make sure you multiply the delta H's by 2, etc., etc. I find Hess's law problems kind of fun, but again, I'm a nerdy chemist, so that shouldn't be surprising to anyone.